All right, everybody, welcome back. We are doing 8.7 today in pre-calc B or trigonometry. This is on polar equations and graphs. And I'm gonna be straightforward with you. Polar equations part is a shitload more important than the graphs part. There's a lot of fancy graphs that can be made. But there's not a lot of, I can't think of a lot of real world applications that go with them. Unless you were trying to make something fancy with like a fucking laser cutter. And you wanted it to follow this neat path. But the polar equation part is really important. Polar equations, we've been talking about polar coordinates and stuff, I mentioned it before. In the last couple of sections, we looked at going from. We had x equal r cosine theta, we had y equal r sine theta. And x squared plus y squared equals r squared for a circle. This is how we relate r to x and y. This is also for a triangle. Oh, and then tangent theta equal y over that. So we've been working when we were doing the whole switching between. XY system and over to. Like r cis theta and shit like that, but there's another use for this. Instead of graphing on something like this, y and x. And we have a bunch of lines. Or grid lines here. And trying to do something like x squared plus y squared equals 4. Here on the, like the left one, we would have to, we looked at going out 2 in each direction, and I know my grid lines aren't matched up very well. So I'm just estimating. And trying to estimate what the curve looks like. It's a circle of radius too. In polar coordinates. We have x squared plus y squared equals r squared. This is r squared equals 4. So r equals plus or minus 2. And there's no indication of what theta is, so theta can be anything. It's any. So on the polar coordinate system, the way it's set up. Is the graph does not have rectangular coordinates. It's got concentric circles. It looks like a bullseye. So maybe I'll use the green to show like the setup on this. It's got concentric circles. Each circle represents going out 1. And they tend to go out a certain distance. And they tend to mark the 30-degree angles and the 60-degree angles. So it's almost like a spider web. In fact, it looks a shitload like a spider web. Other than spider webs tend to tug in a little bit wherever they intersect. They look a little more like. You know what I mean, everybody's seen the spider web. But here it just says r equals 2 and the angle equals anything. So if the angle did matter, we'll talk about doing different angles here. They have one axis and it's called the polar axis. The polar axis. instead. Swap it for a good one. And what we do for polar coordinates is. For polar coordinates. R theta. We. This tends to be the easiest way to do this. You can do it in either order sometimes. But like for some areas, it's easier to think of it this way. Rotate counterclockwise. From the polar axis. A degree or radian theta. And then B. I'm gonna do this in two parts. If R is greater than 0. Go out a distance R on that angle. If R is less than 0. Go the opposite direction. The distance R. So for example. If I have two 60 degrees. I'm going with my circle here of R squared equals 4. I'm starting here on the polar axis. I rotate 60 degrees. And then I go out a distance 2. So 260 is that point right there. If I rotated 2 pi over 6. I get to this point right there. Showing degrees and radians here. Normally you wouldn't have the same on both graphs, but no point in doing them separately. If I had negative 2 60 degrees. I rotate the 60 degrees. The 60 degrees puts me on this axis right here. And then I go the opposite direction too. So I'm gonna come back this direction too. This would be negative 2 60 degrees right there. So if you have a negative radius, which only really makes sense in polar coordinates. You're going the opposite direction. And if I did this for all, since they didn't, it could be any of them. We end up just going out a radius 2. And we're following the circle just completely on it, and we get the same thing we had over here. With x squared plus y squared equals 4. Now we have it as r equals 2. So before we work with more equations, just let me throw some points at you in polar coordinates. And have you sketch them. Hey, wait, people are still writing.
can be negative.
Yes, it means we're traveling the opposite direction. Along that angle.
Oh,
So you rotate the angle that you need, so like 60 degrees puts us at the 60-degree angle right there. And then if I have R as negative, I go the opposite direction along that same line.
it's not that we're going around the circle, it's that we're going back down.
We're going back down. In fact, we're gonna hit the very next topic after we cover like. Making sure everyone knows how to plot this shit is going, there's more than one way to write each point. In fact. There's an infinite number of ways in polar coordinates to write each point. We can keep doing loops, 360, 720, you know. I can go around more and more times, I can go in negative direction, negative angle. So like being able to recognize that. That is helpful. Alright, so. I recommend you draw a big polar coordinate thing. If your circles aren't the best, that's fine, this is a learning exercise. On a test, I will have polar graphs on there. Draw concentric rings, try to make them equally spaced. Doing the inner one first is easiest because it's a small circle. And then you just try to keep your line the same distance from it for the rest. Ooh, that swung out a little wide, there we go.
How many circles?
As many as you want, I did 5. Then I recommend having at least the 60 to 30 and 60 mark. And you're just really just splitting each quadrant into thirds. So whether it's exactly 30 degrees. At least for this thing is not important. On an actual test, you'll have a graph where the computer has made it. So it will have the right angles. But here we're just getting an idea. It's almost easier for me to spin the graph so that I can draw a straight line. God, that didn't look fucking straight. And you just gotta remember like 45 degrees is down the middle of these guys. That's the 45-degree mark. Along the diagonal. I just put that in there for extra bonus. Let's plot the point for 135 degrees. That can give you 3 points. Let's do that, let's do Q equals. -3. Let's go with 120 degrees. Well, point R is. Go with some positive or use some radians. Let's go with 2 5 pi over 3. And why not, let's do. Oh, let's go with S. S will be 2 negative pi over 2. And T will have negatives on both, let's do that. We'll go with just like -5, I'll go all the way out. On our circle here, -5, and we'll go -4 pi over 3. Now let's do -2 pi over 3. There we go. Okay, so for P. I gotta rotate till I'm at the 135 degree mark. Which is 90 plus 45. So we're on the diagonal there. So that's the 135 degree line right there. And we wanna go out 4 in that direction, so 4 circles. That makes that point P. For Q, I rotate 120 degrees and I get to here, that's 120 degrees. And I wanna go -3, which means going the opposite direction. Along this line right here would be coming this way. That would be Q. Five pi over 3 is where? Or 2, yeah, 5 pi over 3. It's on the same line as Q, isn't it? One pi over 3. Pi over 3, 2 pi over 3. 3 pi over 3, 4 pi over 3, 5 pi over 3. 5 pi over 3 is on this line and we're going out a distance 2. R is right there. What are you gonna make about a TPs? What the hell are these?
So this is telling them like, getting all of the interior X and the really shallow small X. It's the over 3s.
Where's S at?
Down.
We're going straight down. And we're going 2. Which should put S right next to R. I just randomly spit out radius and angles, I didn't realize I was clustering them. That's awesome. Alright, so -2 pi over 3 for T. This is pi over, or negative pi over 3. -2 pi over 3 is this angle right here. And we wanna go -5, which means going the opposite direction along that line. Should put T there. This is like being a gunner on a battleship.
It's like this looks like a target.
It's a targeting program, basically.
Yeah.
The circles, like, it looks like a dartboard, but like really, like if you were on a gunship. Your target is at. From point ahead, like the polar axis is basically what direction the boat is going. And like how far do I gotta rotate and what, like, the radius is like how far I gotta shoot out to hit the target.
When the target moves, it moves in one of these angles. You know, it's like, you can track the angle at which it moves and how much.
Depending on which direction it's moving.
Well, I mean, in any direction, if unless it went up, but I mean, if you were tracking on a plane. Any movement would be either a negative or positive along an angle set,
Yeah,
and then you could.
it's either getting closer or further, so your radius is extending or shrinking. And if it's moving, your angle is changing as the target changes. I've never been a gunner on a naval warship, but I get the principle of it. Or, I don't know if they still have them, I know Visalia used to have. There was like tanks you could drive around that shot tennis balls.
Really?
And there was targets on the sides of the tanks. That when you hit the target with the tennis ball, it disabled that part of the tank.
Sounds like a lot.
So it was like literally like you. It was like slow but extreme go-kart. One person would drive around and one person was the gunner, and you'd take on another team, I don't know if they still have them. They were a hell of fun.
That's
But that's the same premise, the tank's driving one way, I've done that. And you got a rotating angle and I don't know if the gun changed direction or height, but the gun swiveled.
yeah, I was gonna say, they usually just have two, it's this way and it's up and down.
Right, it'd be up and down and rotate. Up and down is giving you your R. Based on gravity, but. Alright, so let's look at what we can do. With this to look at alternate forms. So like each point has 2 or 4 alternate forms that are fairly easy. So alternate forms of polar coordinates. The principle or idea here is. If we have R theta. We can use any R or the same R with any theta plus or minus 360 degrees. Or 2 pi if we're in radians. And we're gonna hit the same point. We're just rotating around the circle one more time. If you're the gunner on the tank, you're getting fucking dizzy if you've gone too many circles.
Screw the tank top, actually.
It's fucking, yeah. I haven't. I wanna say I was 20 when I did it, so it was a long time ago. I don't know if they still have them. I don't even know, fuck, I didn't live in Visalia when I was 20, so. I don't even know where the hell I'm fucking talking about.
I was gonna say, I'm like, I haven't heard of this, would be fun, I was like, yeah.
That reminds me of like a spot in Visalia, so I don't know, maybe I'm tripping out. Or. Or we can not change the theta, or we could do negative R. And do theta plus or minus 180 degrees. Or pi. So we go 180 degrees more different than the angle we wanna do and go the negative distance. How does that work with P? P was 4 and 135 degrees. So I could write this as 4. Oops. 4 and then 135 plus 360. Which is 4. Is that 495? Most times we don't do that. We tend to. Aim for. Negative 360 to 360. So going more than one loop seems ridiculous. So like, I'm gonna say that's probably one we wouldn't use. But if we did the minus. What am I getting here, 225, negative 225? The other option is, and so this is one I would likely use, I like this one. This is between the negative 360 and 360, I like it. Then we have the -4 options. We're gonna do 135 plus 180. And 135 degrees minus 180. This is -4. 315. Positive, yeah, 315. And this is -4. 45 degrees.
It's -45 degrees.
Yeah, it is a minute negative. Good catch. So this one and these three are the 4 primary different ways to show the same point. Usually we don't go above 360. Normal humans don't, cause if it's above 360, you just. Subtract 360 and get back down to a normal circle. I gotta look up to see if they still have the same thing, maybe I'll do this on break. They're fucking hell fun. Take out some buddies, you're all safe, you're in a tank. And it's not shooting mortars, it's fucking shooting tennis balls. And you know when you've been hit, cause your shit. You either can't fire, you can't rotate, or the tank can't move. That's a great way to do it, I think the idea is to disable the entire tank. But I think generally they let you play for like an allotted time frame, not until you take out your opponent. It's more fun when there's more than 2 tanks. God, that shit was fun.
So it would be fun to play that against like some paintball, like some guys with paintball guns, like that would be a cool counter.
You fuck them up, fucking launching tennis balls at them, how much it would hurt? Paintballs fucking hurt.
Yeah, I was gonna say, like, it's
That shit leaves fucking bruises. That thing's that's. You know when you've been hit, you know when you've hit somebody,
Yeah.
cause generally they gotta fucking flinch when you get a hit that hard. Why don't you guys try to do the same for, who wants to? Pick a letter, Jordan, Q, R, S, or T. Let's do S. Find 3 other ways to do S, oh you slacker. Chose the easiest one. Find 3 other forms for S. And T. I go with a fucking 90-degree one, that's just cheating. Give me a few minutes to do that, in fact, I'm gonna look up. See if I can find the tank thing.
You sort of stay in meetings.
Stay in the radiance. Only one is popping up and it's cause it. People got hurt there. The one that's popping up the most is one that is in New Jersey, and I know that's not the one I went to. Cause I hadn't been to New Jersey until I was in my thirties. Apparently, like, if you got stuck, and you couldn't get out of the tank. If you got stuck, that wasn't the problem. Someone would have to go in to try to get you, and other assholes would shoot at the fucking person running out there. And it's not like aiming with a fucking golf ball, trying to hit someone on the golf course a long ways away. You're using something that's pretty, has better targeting and shoots faster. And so people would get, I don't know.
Yeah, but that's kind of like what we do, I know one thing we do have over here. Is we have archery tag. So we have in Lindsay, that big place over there, for a while they had archery, I don't know if they still do, but it's this idea where there's foam tips on arrows. So
Okay,
you can basically shoot arrows at each other, and it's kind of like arrow dodgeball, like arrows move slowly enough that you can see them, so you can grab them out of the air. So it was a pretty fun thing, like it was like, I played it a bunch of times, but the problem is that the tips were round enough that the arrows would hit the ground, and if you were running between cover, you could step on one end of it and the other end would pop up, and the sharp knock that you used to get into the arrow is still there, so it would pop up and like stab people.
like stepping on a rake kind of thing.
It's kind of, yeah, it's people get hurt, so it's like, this idea doesn't work well.
Actually, it's in my head. Gotta get it out of my system and then we'll. Do something like this. But the picture was there better on the other screen. They'd have targets on the side of them. And you're aiming at them and like there's targets up here and. With a gunner thing on it. It was fun. I can see why they stopped doing it. If people were fucking being assholes and trying to shoot fucking civilians, like the people helping you. Alright. Where's like, I gotta go pee right now. Alright, so what'd you guys get for S?
Yeah. 2 and 2, 3 pi/2. And -2 pi/2. And -2 negative pi/3. Oh, negative pi/2. Oh, -3 pi/2, sorry.
Yeah, that sounds better.
Wow.
It's still technically an answer, but I'm just saying most people wouldn't use it. What about T?
We got -5, then 4 pi/3 is one answer.
That seems like a valid bingo to me. Anyone else wanna chime in? Or do not Lydia, Jordan and Davis have to do all the talking in here?
+5 pi/3.
There we go. Anybody else wanna bring me home for the last one?
+5, -5 pi/3.
There we go. Thank you, Owen. This idea is like literally the most important part of this. We are in like the latter half, I'm gonna do a little bit more first, we're switching between polar equations and. And rectangular equations, that's a useful skill. In terms of what we're gonna do in the last half, the graphing of weird shit. I can't say I've ever used it. Beyond. In this class, what we're doing. But it is neat. And if there is something, I'm not an engineer, if there is something, I'll at least have shown it to you. But I probably won't test you on the weird shit that's coming up in a little bit. You will be tested on polar coordinates, it's important. It comes up in Calc 2 and Calc 3. A lot. Calc 3, we shift from polar to. What's a three-dimensional circle? Sphere, we switch to spherical coordinates. We do use polar coordinates in Calc 3 for cylinders. Sometimes rather than trying to use an XYZ coordinate system on a fucking soup can. It's easier just to rotate out an angle. Go up a certain height, or go out a radius and so up a certain height. So it shows up in. Calc 3 the most, Calc 2 at the end, you like refresh on it. At the very end. I know, cause I'm teaching it today, and like someone else was teaching it yesterday, and they were bitching about it in emails that students didn't know in Calc 2 polar.
Well, there's those, thing that comes to mind there is, well, the cylinder, example is those, the car vending machine idea. You probably might have seen this. But
What the fuck?
yeah, it's a giant tower that's just like got 1,000 cars in it. It's a whole thing that they did in Texas, it's old. But they, it's crazy, but you would need a targeting, it has a giant lift that has a targeting program that.
Okay,
Scoops them out, it has to know all the distances to the arm, the aperture, that moves them down. To have a scoop they can grab it.
I'll show you a little bit, but I'll give you a sneak preview so like you have more motivation to remember this. Cylinder. So like, let's say. I'm gonna put X in here. Often we do X in 3D, we do X out of the page. Y is this direction, so X is out of the page. But you can't really show out of the page in a 2D drawing. And Z is upward. So like an overhead view. Is just a circle. And it would look like X this way and Y this way. So when you're doing cylindrical coordinates. You start here. It's easier kind of to view down here. Wait, this is the X thing. You rotate an angle theta from it. So like, let's say we're going pi over 3. We go out a distance R. And then we go up a certain height. So like if this full thing is H. And this is at the center, then half the distance is H over 2. And this point directly above the y-axis would be 90 degrees. So this point would be R, whatever the radius is, 90 degrees, and then H over 2. So it goes R theta Z. Z is for height. That's cylindrical coordinates, you're not gonna see it again until Calc 3. But we do a lot of shit with it, so like this stuff does come back. Until then, let's take a look at switching between systems on equations. Let's say I have y equals 2x minus 4. Obviously easy to graph. In rectangle. If you don't know how to graph that line. You're fucked when you get calculus. Like if you don't remember, fucking spin this spend winter break going over some shit. In fact, I will give you guys all a little flyer, it's like a 100-page pamphlet. Of all like a common algebra and trig that's gonna pop up. In calculus. I'll give it to you guys I'll put it up as on Canvas at the end of the semester, the digital thing you download. So like if I wanted to switch to polar, which is where it's gonna be shitty to graph. I have to start substituting in things I know. Y is listed as r sine theta. And x is listed as r cosine theta. Just like we will tend to write equations where like y is in terms of x. We usually write r in terms of theta. So like isolate r. So to do that, I can subtract 2r cosine theta from both sides. And I factor out an r. And then I divide through. By this stuff being multiplied by r. I'm not a big fan of having a negative sign in the numerator, so. The alternate form is to move the negative down below. And that just makes the cosine theta term positive and the sine theta term negative. So this is graphing the line y equals 2x minus 4. In terms of theta, you kind of have to plug in thetas. So like if I did theta equals 0. R equals 4 over 2 cosine 0 minus sine 0, which is 2. I'm going on a distance 2. I'm gonna say 0 degrees, not just 2, 0. If I wanted to, let's do theta equals 40, shit. Let's do theta equals negative pi over 2. R equals 4 over 2 cosine negative pi over 2 minus sine of negative pi over 2. That's 0. This is minus 1, so 4 over 1 is 4. When I go negative pi over 2, I go outer radius 4 and drop a point. Obviously, this gets kind of shitty when we try to do other angles because it's calculator time. If we tried 45 degrees. 45 degrees should be right there. Well, now this is a shitty problem. 2 cosine of 45 minus sine of 45. I need a calculator. If I tried to do this in radians or with the radicals, This is square root of 2/2, which is times 2 is square root of 2. Minus square root of 2/2. Even if I clean this up. This is. 8/√2. Which is 4√2. That still doesn't help me, I don't know how far that is on the radius. So you actually need a calc, I think ahead, right? Like if you multiply by 2/2 on each.
Do you move it up a little bit?
Oh, on screen. That's what the weird books are for, got it. Multiply by 2/2, this becomes an 8 on top. This fraction clears, this one doubles, I got 2√2 minus 2. Gives me √2 on bottom. And then if I rationalize, I get. Multiply top and bottom by √2. I get that. 4√2 doesn't help me though. So what is that? 4 times square root of 2. About 5.65. .66, I don't know. Is that 5.66? So like doing this one is shitty in polar. Right? Other ones aren't. Yeah. Let's take a look at. Y equals. The square root of 9 minus x squared. If I convert this to polar, you're gonna see how easy this is. We're gonna have r sine theta. Equals the square root. Of 9 minus r cosine theta squared. This one, unless you know what this shape is, you kind of gotta make an XY table. Start plugging shit in and figuring it out, right? It's gonna be a lot easier when we switch to polar. If I square both sides. I get r squared sine squared theta. Equals 9 minus. This square I'm gonna distribute. R squared cosine squared theta. And then the square root and the square cancel. So square root and square cancel. And then here I just distributed this square to get that. You guys with me? I can add. R squared cosine squared theta to both sides. Factor out the r squared. What's going on here? What can I do? Sine squared theta plus cosine squared theta is 1. So I just got r squared equals 9. Which means r equals 3. I could do the negative version if I wanted. That doesn't have a theta, so it's a circle. But there is an implied theta. From here. Y is equal to the square root, so y is greater than 0. Which means r sine theta is greater than 0. And if I divide it by r. Sine theta has to be greater than 0. Which means theta is going from 0 to 180. Or 0 to pi. Which means it's a circle of radius 3, but it's only the top half of the circle. Alright, let's take a 10-minute break and then we will do the. Shit that's mostly useless. As far as I know of, but I think it's fun to do, it makes neat graphs. So here we've got some polar equations. R written in terms of theta, where A is a constant. A is some constant value. So our normal circle is centered on the origin. But if we wanted a circle that's not centered on the origin, shifted like to the right. We're cracking up about.
The icons, sorry. It's like, they're like the third, like kind of libertarian. It's like-
These have actually other names, like these two are called cardioids in the middle. Not just limacons, but cardioids, because they have a fart-like shape. It dimples in on one side. So like, you're not gonna memorize these shapes, I'm just kind of showing them to you. I will scan this with the lecture notes. So you can have a shape of it, but like something to note is. These ones tend to be like the harder ones to do, but they're more fun to draw. And you will notice that when n is even. If n is even. You have 2n leaves on your rows. And when n is odd. Oh shit, I got it written up there. When n is odd, you have just n leaves. But it goes out like a specific distance on each one. There are applications where this matters, like. This looks like a fucking propeller. Right, if I made it longer radius. A bigger A is just gonna push this out. But it still has to come down here, so like a bigger A is gonna make it flatter. And be more propellerish.
Is it A area?
No, A is like a constant, it's like the amplitude. It's a constant. Rather than writing in 2 or 3, like, it's just for any A. Any number. But it's the same number for the whole graph. The number is,
So it's a constant, but it has to be derived from each. It's not like our number. Constant.
right. Like this might be maybe. R equals 2, I don't know. Or A equals 2. And here A might be 4 where it's flat, like longer out. We're gonna do some examples right now. And you really don't need these to know these to do them. Because like, this isn't all that helpful. This speeds it up, if you know, memorize these. You have much better shit to do with your time than memorize these, because you don't hardly ever use them. But the easiest way to go about these, to graph these. Is to just make a chart. Let's do R equals 1 minus sine theta. So what I'm gonna do is I'm gonna make a chart of theta. I'll make a column for theta. Then I'm gonna make a column that has sine theta. And then R is 1 minus sine theta. And if you can, do like every 30 degrees. You kinda wanna go around the whole goddamn circle though. Maybe I'll put in. Some dividing lines so we can see where everything is a little bit easier. I'm gonna ask Mr. Allen, Professor Allen. He's our engineering teacher here. If anyone does it anywhere, it's in the engineering course. I know it wasn't in physics.
I wonder if it maybe could do with more openness.
You might be able to use it in chemistry to graph fucking or plot the paths of electrons, but. I don't know any chemistry students that are doing fucking this shit. This is like too much math for fucking chemistry students. They struggle with fucking algebra. They're like, it's too hard math, why is there math in this? You're just balancing the fucking chemistry equation, it's not that fucking hard.
It's like most of the addition. It's
Right.
It's pretty wild, it's like.
Alright, so 0 degrees, we have sine theta is 0. And so R equals 1 minus 0 is 1. Do you guys wanna plot these on the graph as we're going, or do you wanna just find the whole table first? Whole table?
Yeah.
Okay. What's sine of 30 degrees? 1/2. I can do this one without a calculator, 1 minus 1/2 is 1/2. Sine of 60 degrees is √3/2. Am I in degree mode? I am in degree mode, excellent. So I'm gonna do 1 minus sine 60. (0.13). Sine of 90 is easy, that's 1 and 1 minus 1 is 0. I'm going to stop filling this out, you guys know how to fucking do this shit. You guys do it all together and then I will write all down. Like. Give you some practice doing this. That way we don't have to do as many of these. Like a fun one to do next. One minus it was up, one minus a negative is plus.
This looks oddly like the waveform.
I have no idea what you're talking about.
The sine wave.
Well, it should, we're basing it off the sign. Like, the fucking values do oscillate between -1 and 1. Alright, so let's plot this out. It looks like my biggest radius is 2. So I'm just gonna do 2 circles. That's not a bad three-handed circle, look at that. That one's slightly less good. And now I'll put in the diagonals. Maybe I'll do them as like dash lines so they don't take away from my beautiful fucking drawing. For me, I need to rotate this to do these. Otherwise, they just look like shit. So when we have an angle of 0, my radius is 1. When I have an angle of 30, my radius is 1/2. (60 degrees) is 0.13, so like close to the center. I'm gonna start drawing a curve with it as I go. Cause if I don't, I might lose track of where everything connects later on. It's a good idea. Especially with some of the bigger ones. When I have a 90 degrees, I'm at a radius of 0, which puts me at the origin. R equals 0 means I don't extend out. 120 degrees is 0.13, we're back out a little bit. 150 degrees, we're out halfway. And at 180 degrees, we're out 1. Let's see, 210, we're at 1.5. So we're starting to go outward. 240, we're close to the second ring, 1.87. And at 270, we've made it to the second ring. And you'll see these are often symmetrical in a way. I have a nice little heart shape. I think the extra credit problem is gonna probably be one of these. Fucking not hard. Well, don't smear it, Dad, this is easy points. Just gotta make a fucking table and plot them. You're gonna have to know how to do polar coordinates anyways, that will be on the test. Graphing it is just doing a bunch of them and doing it. So I'll show you like setup, what you should be doing for other types of setups. We'll do one more graph in particular, but I wanna show setups for other ones.
And it's the full graph.
Yeah,
They are the same.
Yeah.
You know, your X and Y still are exactly what.
what is this in terms of X and Y? Let's take a look at that. So we have R is x squared plus y squared, square root. And sine theta. We had y equals r sine theta. So sine theta is just divide by r. Sine theta equals y over r. But r is square root of x squared plus y squared. So if I were to clear fractions. On the left, I would get x squared plus y squared. On the right. I would get square root of x squared plus y squared minus y. This looks like a bitch, doesn't it? It's already a bitch. If I wanted to actually get rid of the square roots, I would probably add y to both sides. And square this. Squaring that is ugly. Right side's easy though. Left side, I would need to multiply out. In fact, this is a good practice, let's do it. I've got an x to the fourth. I'm just distributing one at a time, I've got an x squared y squared. And I've got an x squared y. And then I distribute the y squared, I got a y squared x squared, which is the same thing as that. Y squared is y to the fourth. And y squared y is y cubed. And then I distribute the y times x squared is yx squared, which is this one again. I've got another y cubed and a y squared. So if I add those all up, on this side, I've got an x to the fourth. Plus 2x squared y squared. Plus 2x squared y. Plus y to the fourth, plus 2y cubed. Plus y squared. That's a clusterfuck, if I've ever seen one. Wasn't that fun? It's good practice on your algebra.
Yeah, it's just, maybe.
I should have done this with more room on the page.
It's you know, that formula.
What?
This breakdown for the test.
Doing this part, you should be able to do. Switching between polar and rectangular is something we need to be able to do. We did a couple examples earlier with like y equal to 2x minus 4 and. We practiced going that way. Alright. The next one, I'm gonna set up the table, but we're like not gonna graph it or completely fill it in. In terms of interest. When you have like a rows graph. Something like. R equals 4 cosine of 3 theta. I think I actually have this graph completely like in a lecture video in a previous course. So you can look at the full graph of it there. I would recommend on your table doing theta. Then cosine theta. No, not cosine theta, 3 theta. Because that's what you're sticking in. Cosine. And then finding R. So I'll do a few lines of this. And I'm actually gonna do less degrees because. Tripling it is gonna, like if I do 30 degrees, we're jumping to 90-degree increments. That's not gonna help us see what the graph looks like. So I would do. Like if I was doing 30 regularly, divide by this. Divide by that, 30 divided by 3. I'm gonna do like 10-degree increments along here. So that I get 30-degree increments along here. This is how you think ahead. Play the smart game, otherwise you're not gonna have enough points that make it realistic looking. Cosine 30 is square root of 3 over 2. Cosine 30 is 1/2. And cosine 90 is 0. Maybe I should have the 0 degrees in there. And so when I do R, this is. 4 times that is 2 root 3. That's about 3.46. I do R here, 4 times 1/2 is 2. I get a 0 here and that's a 4. A quick sketch of that. That's the 30-degree mark. So all of this happens between there. You're going off of this column and this column. Don't go off the 3 theta column when you're sketching. So like 0 degrees is out 4. 10 degrees is out like 3.5. Maybe this would help if I drew like concentric circle here. So 10 degrees is like 1/3 of the way through, that's about 3.5. When I go 20 degrees, I'm out 2. And when I go 30 degrees, I'm out 0. That's just doing the first part there. When you're done, you're gonna have something that's doing this. And the one that I think is more fun. That looks shitty, it should be more evenly spaced, it should look like a 3-leaf clover. One that's a little more fun to look at is R equals negative theta. This is called the spiral of Archimedes. I'm gonna start like do a sketch of this, I'll start at negative pi though. theta. Negative theta, which is R. So negative pi makes this pi or about 3.14. Negative pi over 2. Makes this pi over 2. If I'm going to one decimal place, this is close to 1.6. I'm doing bigger increments because you'll see what's happened with this. Quickly, that's about 0.8 at the previous number it had. Zero is zero. I don't know, pi over 4. Is negative pi over 4, so negative 0.8. Pi over 2. Get all our values above, I'm just making it negative. I can go bigger steps here for the last few, let's do 3 pi over 2 and 2 pi. And that's about negative 4.17. Negative 4.7, I should say. I made 6 rings. I'll just go a little bit past it for the other one. So when theta equals negative pi, I'm going out 3.14, negative pi is over here. 1, 2, 3 is a little bit past it. Negative pi over 2 is down here and it's only like 1.6. So between ring 1 and 2. Negative pi over 4 is less than 1, so it's like right about there. And we get 0, 0 there. So I got something doing something like this here. And when I go pi over 4, I go negative 0.8, which is backwards. When I go pi over 2, I go negative 1.6, which actually puts me down to where I was before. And when I do pi, I'm at negative 3.14, which is like the opposite side of the circle over there. And when I do, let's see. That was pi. 3 pi/2 is going all the way around here and it's -4.7, so. 1, 2, 3, 4, right about there. We're coming up to here. And 2 pi is going all the way around. And we're at -6.28. Which is over here. If I went the other direction, I can see it's symmetrical. I could rotate the other direction and do this. But we can see it's going outwards, but it has to circle back around. Cause we would keep re-hitting the same theta. If I did 3 pi. 3 pi is about -9.45. 42. 1 pi, 2 pi, 3 pi. -9.42 is coming way out over here. It looks like it, or was 2 pi? 2 pi was over here. 3 pi is getting us. I don't know how we get there, somewhere like that, we're spiraling outwards. It's making a bigger sweep. Just keeps going further out. It's doing some shit like that. But then when you do the negative theta, it's doing the opposite direction. That's called the spiral of Archimedes. Kind of neat. Let's give another example of converting between polar and rectangular, just so we get a little bit more practice in there. Because we did it on one of the examples a little bit ago. Polar to rectangular. Let's say we had r equals 1/1 minus cosine theta. I'm gonna clear the fractions and have r times 1 minus cosine theta here equals 0. And we did 1/1 minus sine theta earlier, and we did it, took a little bit longer. Cause I switched right away. There is an advantage at this point to, instead of jumping straight to it, recognizing. X equals r cosine theta. Oops. This might be easier if I just multiply by r. No, I actually distribute, what am I saying? Distribute, I got r minus r cosine theta. Being a scrub. Not paying attention. I said 0, there's a 1 over here. And now when I switch to x's and y's. X squared plus y squared. Minus x equals 1. Leaving it with the square root is bad form. So I'll add x to both sides. And let's square it. Remember, this is x plus 1 times x plus 1. That leads to x squared plus 2x plus 1. So if I subtract x squared. I get y squared equals 2x plus 1. If I factor out the 2. I can see where the vertex is. This is a parabola. This is a parabola that opens to the right. And the vertex. If you remember your algebra, is that this will be at -1/2 0. Which I think is easier to graph than this. Here you gotta go through and do that whole table of thetas and shit. Any questions? I think I threw enough shit at you for today, we'll see what sticks. Have a good day, GTFO. Got one more section.